Hi everyone. Today I'll be presenting our work on stress effects in semiconducting metal oxide materials on MEMS-based gas sensors. Understanding the effect of mechanical stresses plays an important role in reliable functioning of MEMS sensors and actuators. These stresses may arise from several factors like thermomechanical stresses or external forces like shocks and vibrations during its operation. In this study, we have tried to demonstrate the importance of studying the stress effects in SMOx materials and its implications for a typical MEMS-based gas sensor's performance. To understand the effect of stresses induced due to CTE mismatch in the MEMS layer and between the MEMS and the package, we did a simulation on Comsol on our proprietary MOX-based sensors with its package. We see that for 1 degree shift in the ambient temperature, the strains in the heated bridges with the gas sensitive material printed can change by 7.5 × 10⁻⁴%. SMOx inks were printed on the glass coupons with self-built picopump robotic arm as shown in figure 2. A nichrome wire coil heater is used to reach higher temperatures up to 350 degrees Celsius at which the SMOx based inks resistance were observed. SNO2 particles, which are most commonly used SMOx gas sensing particles, were used in the experiment to understand the effect of stress on change in the resistance of these printed thin films. Borosilicate glass was chosen as the material or the substrate in this study as glass is very commonly used MEMS material and is thermally insulating in nature. A 4-point Flexure test setup was created to apply stresses to these glass substrates as shown in figure 4. Using this setup, we ensured that uniform strain can be applied on these SMOx based printed particles. As shown in figure 5, the stress will be at its maximum compressive value at the edge of the concave face as shown in point A, and at convex face of the specimen, point B, the stress will be at its maximum tensile value. The experimental setup used to understand the effect of stress on the resistance characteristics of these SMOx particles is shown in figure 6. It consists of a 4-point Flexure setup, a heater power supply for the heater, and a multimeter to record the change in the resistance of the SMOx pattern for an applied force. 3 inks were created using SNO2 particles of different sizes, 17 nanometers, 42 nanometers, and 450 nanometers in glycol solvent mixture. Strain was applied in steps of 0.05% to the SMOx materials while the resistance of the printed patterns were continuously monitored. Figure 7 shows the step response of delta R over R as the strain values are increased in the steps of 0.05%. Figure 8 shows that the dependency of the particle size to the relative change in the resistance with the applied strain. In all the 3 cases, the delta R over R response to strain is very linear and is reducing with the increase in particle size of the SNO2 particles. To know more about how these results can have a significant implication for many gas sensing applications where detection of low concentration are very important, please visit our poster.